So this is rotational motion test practice number 7. We've got a penny on a turntable. The coefficient of static friction between the penny and the turntable is 0.55. At t equals 0, the turntable begins to accelerate from rest with an angular acceleration of 0.75 radians per second squared. First, we want to find the maximum angular speed with which the turntable can rotate without the penny sliding off the turntable. And then we want to find out how long it would take for the turntable to reach this angular speed, given that it started from rest and it has an acceleration of 0.75 radians per second squared. Okay, so first we have to figure out how fast it can go, how fast it can spin, without flinging the penny, essentially. The penny needs to stay on there. So when it is up to speed, essentially we will have a thing of mass m going in a circle with radius of 0.14 meters. It has some linear speed at that time, and we are looking for the maximum linear speed. We're looking for the maximum angular speed, but we have to find the linear speed first to do that, so that's what we're going to do. So the best thing to do is always a free body diagram. You guys know it, always a free body diagram. So the penny, we're going to do like a side view of it. So here's the penny. By side view, I mean so you can see the force of gravity pulling down on the penny. Whoops, sorry. Ooh, how do I put that back? Just a second. Found it. Okay, so we have the force of gravity pulling down, and we have the normal force pulling up. And we have the static friction force pulling the penny toward the center of the circle. There has to be some force doing the job of centripetal force if this is moving in a circle at all, and the only thing available is the friction, so that's it. And it makes sense. Friction is always parallel to the surface, and this is the direction parallel to the surface of the turntable. So that's it. Nice thing here is the normal force and the weight should be the same because there aren't any other forces involved. This is nice flat surface, so they don't have to worry about an inclined plane or anything. And we don't have this penny accelerating up or down because that would be weird. So the acceleration is 0, which means those have to cancel, which means they're the same size, which is good. Because we are eventually going to need this expression here that static friction is less than or equal to the coefficient of static friction times normal force. And in this case, the normal force, did I put in, I guess it'd be, just rewrite it, less than or equal to mu, the normal force would be mg. Okay, so we're going to use that later. We'll talk about that in a second. So, time for a Newton's second law. Always. That's where you always start. Okay, so this penny, in the x direction, the only force acting on it is the static friction. So that is the net force. Boom, boom, that's done. And the acceleration is the acceleration needed so that this will move in the circle. That means it's going to be centripetal acceleration. We do need to check some signs. I didn't put any signs on here. Let's just make to the right positive, which means that's toward the center of the circle as well. So the centripetal acceleration is also positive. So, positive, positive, we're good. So here's the thing. If you put in the equation for centripetal acceleration, which is v squared over r, this will give you the static friction necessary to go this fast around a circle of that radius. If you want to know the very, very fastest that you can go, you will have to use, so you're trying to find the maximum speed, you will need to use the maximum friction too. So that equation that's a less than or equal to, static friction is less than or equal to all this stuff over here. If you want to use the maximum, then you're using like the equal to part of that, okay? Which means that your static friction is mu times normal force or mu times mg. Okay, Then on the other side, oh, I squished this a little bit, sorry. We'll go like that. On the other side, we still have the other stuff. Note, we have a nice m on both sides. They go away. This is good because I never told you the mass of this penny. Okay, so that means that multiply both sides by r to get v alone. R mu g square. I'm not going to square root it yet. Okay. This will give us linear velocity, but the problem didn't want linear velocity. The problem wanted angular. So we have to make a little bit of an adjustment with one more equation here. So we also know that linear speed equals angular speed times r. So I'm going to replace that in here, and that will give me r equals mu, oops, what the heck, no. Sorry about that, I don't know what I was doing. Okay, equals, hang on, I'll put that back, but I just need to put that. Oops, that's not right either. Man, I remember how to do this a second ago, and now I don't. Poop. Found it again. Okay. 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 So I've got this. Well, now I've got an r on both sides too. Or rather, why don't I just divide both sides by r squared? Oh my goodness. Okay. Okay. I found it. You go to actual size. There's a button on the stylus I'm working that's like, I keep hitting with my index finger, and that's what it's doing. That's what keeps happening. Okay, so that's going to cancel that. And alrighty, and so what I end up with is when I do all my algebra out, I will get that the square root of mu g over radius will get me omega. If I put the numbers in, I'm not going to show that, but it does come out to 6.2 radians per second. Okay, so next I need to figure out how much time it would take to get to that speed with this acceleration and starting from rest. I do need a little room, so I'm going to delete some stuff. All right, got the room now. So let's get a new color here. How about a purpley kind of a weird, yeah. So on your equation sheet, there is an equation. It's a kinematics equation that your omega at a time t is initial angular speed plus angular acceleration times time. So that means that the time will be omega minus omega naught. Did I say that right? Yep. Divided by acceleration. Well, omega naught is 0, so we're going to make that a 0. It's going to go away, which means that the time will be omega over alpha, and that's it. Put those numbers in, 6.2 radians per second. Oops, did it again. And that one's not too far in, so we'll just go with it. And this one was 0.75 radians per second squared. So note the units do work out. The radians will cancel radians. This second on the bottom of the top, that sounds stupid. This one on the bottom of the numerator cancels one of these on the denominator of the denominator, which is going to flip it over and give you seconds as the answer. Anyway, the answer comes out to 8.3 seconds. That's how long it will take. If it continues to accelerate like that, in the very next moment, this thing will go so fast that the static friction will break, and and I lost it again. Where is it? This one. Okay. The static friction will break, this thing will slip, and it will fly off in its current tangential speed, that way, tangential velocity. And, that's not what we want. So, yeah, that's it.